Hello and welcome to this episode of SPSS one-on-one series with the World Analytics. Today we look at negative binomial regression analysis in SPSS. In our previous episode, we looked at Poisson regression analysis in SPSS. So today we are using a data set that is similar to what we used in Poisson, but this one has been modified a bit to fit negative binomial regression analysis demonstration. I've put a link in the description of this video where you can download this dataset for your practice. So in this dataset, we have an event count for Poisson regression. Remember, we should have a count outcome with a non-negative value. So we have a count outcome here. We have three variables, that's age, gen, and pollution level, that we want to use to predict the outcome or a visit to the doctor. So as usual, whenever you're building any model, you start by checking for assumptions, then build the model, and then do a final model check. So in this data, we shall start by checking for our assumptions, and the major assumption when you're choosing between either to use Poisson or negative binomial regression is checking whether the mean is equal to the variance. If the mean is equal to the variance, you go back and use Poisson regression analysis. If it is not, then negative binomial regression is there for use. So we shall start by running the simple descriptive statistics. Go to analyze descriptive statistics and then choose frequencies. We want the variable event outcome, which is our outcome variable. And then statistics, we are interested in the mean and the variance here. We forgot to uncheck the frequency table, but it's okay. We need to see from this, clearly we can see that the mean is not equal to the variance. The variance is higher than the mean. And this is a term we call overdispersion. When there is overdispersion in your data, then negative binomial regression has that flexibility to correct that overdispersion. Instead of using Poisson, we use negative binomial regression. But we can also go ahead and test whether this is truly not a Poisson. Remember, these two models move hand in hand. So we can go to analyze non-parametric tests, legacy dialogues, and then we choose the one sample KS. In this, we want to test this outcome variable, whether it doesn't follow Poisson regression. And our mean here is 6.97, so we shall have to specify here 6.97, and then click. Here we are interested in this last table, the one sample Kolmogorov-Smirnov test 2, which is testing whether is this distribution Poisson. The null is that the distribution is Poisson. So when we have a significant p-value here, it indicates that we reject the null hypothesis, which is telling us that this is a Poisson. In other words, this data doesn't follow a Poisson distribution. Therefore, we can proceed with our negative binomial regression model. So the next step in model in analysis is now building your model. We are going to build our model on this data. We've previously covered the three major steps that you have to follow when building a model. That is selecting which variables are you going to include in the multivariate analysis. Sometimes you have very many variables. Second step is checking whether there is interaction among your independent variables, and then checking for confounding before building your final model. We are not going to assess this because we have previously assessed them in detail under logistic regression, binary logistic. So I highly recommend that you go and watch that episode to get a better understanding of these steps. So we are going to assume our sample size is adequate enough for us to run our model. So to set the model, we are simply going to analyze, then go to generalized linear models, and then let me reset everything here. So in this dialog box, we have different tabs here. We shall be looking at one at a time, but the first one specifies the type of model. Depending on the type of outcome that you have, here we have a count outcome, and we want to use a negative binomial with a log link. I would choose this, but I'm not going to use this because it sets the dispersion parameter to 1, which I don't want. So I'm going to use the custom and then choose the distribution, which is negative binomial, and the link function, which is a log function. And then I'm not specifying a value, but instead I'm estimating a value. If I leave this at default, it is equivalent to using this option. So I'm going to choose this estimate value. And then under response, we are going to put our outcome variable under the dependent box. And then predictors, we are going to use categorical variables into the factors. And then we use age as a covariate. Okay. Then under model, we are going to use all these factors as main effects into our model. Okay, and under estimation, we are leaving it as default. Statistics, we are going to choose one additional box here for including exponential parameter estimates, and then we leave everything as it is, and then click OK. So the output is similar to what we saw in Poisson regression analysis, and the interpretation is the same. However, here we can see that we are modeling event count using negative binomial with the log link function, and our summaries are here, our categorical variables, okay, our numerical variables, the descriptives, and then we come to the goodness of fit table. This one is a table giving us results for dispersion in this data. We are interested in a value as close to 1 as possible, because that's the one that shows that variance is equal to the mean. Different books recommend between 0.1 to around 1.1 as a good value. Okay, so the closer to 1, the better. Here we are not doing badly. The omnibus test, this is a test that tests how good is your model. It compares the null model without any predictor variables and the model with your independent variables. We are interested in a significant value, which indicates that our predictors have significantly improved our models when we put it there. Then we have here a test of model effects, showing you which of your variables is or are statistically significant. When we look at this, all our 3 variables that we are using are statistically significant, and we can go ahead and interpret the parameter estimates table. So we have the parameters here, the categorical ones here, 0, 1, and then 1, 2, 3. They are using number 3 as the reference category. Even here, 1 is the reference category, the highest coded, but I may not be interested in using that. I want to reverse the reference categories. To do that, I can simply go back to where you build your models from. Generalized linear models, and then under predictors, you go to options and you choose descending order. Then click continue and then click OK. We go to our last table here. You can see that as opposed to what was previously 0, 1, 1, 2, 3, now we have 1, 2, 1, 0, 3, 2, 1, and now the 0 is the reference here, and level 1 is the reference category. So we can interpret, usually betas are problematic to interpret because these are not interpreted directly, because here we are looking at, for a numeric variable like age, we are looking at a natural log of the risk for every unit increase in age. Whereas for categorical ones, we are looking at the natural log of risk when one group is compared to another, keeping all the other factors constant. But generally, when we have a positive value, it means that variable is positively associated with our outcome. If we have a negative value, then that means it is negatively associated with our outcome. So when we look at these positive values, initially before we changed the reference category here, they were kind of negative. Okay? To understand this, let us first interpret the exponents of beta, the risk ratios. In this model, these are risk ratios as opposed to odds ratios that we saw in logistic regression. Okay, so here we start with this numeric variable, age. So we say for every unit increase in age, there is a 2.2% increase in the risk of visiting a doctor. For a categorical variable like this one, remember this is the comparison group. So these two groups are being compared to the reference group. So we can just say there was a 55% increase in the risk of seeing a doctor among people with exposure level 2 compared to level 1, keeping other factors constant. Same thing here, we would say, maybe we can interpret for this gender. There was a 64.4% increase in the chance for females visiting a doctor compared to males. When you look at this 2.361, this is showing that it is over 136% increase in chance. Using this example of gender, we are saying females have a higher risk compared to males. So if we change the reference category and we make the females the reference group, it means males are less, males have a less or a lower risk. That's why we are seeing when we reverse, we have a negative here, and even the risk ratio here is less than 1. So next we look at how do you present such results for your research output. So this is how you can present your results. You feel free to pause and read through. So next we shall be looking at a scenario where we have an offset variable in either Poisson or negative binomial regression. How do we handle it? So see you in the next episode.